enjoy according for you. Give your report. What time is the dinner, by the way? 6. 6 is late. Tea time. Counter's crazy, but not so much. Okay, please.
We go. So, hello everybody. So today is a real day on the problem of tumor growth, and it's exceptionally it will be a work I did myself. It's very unusual that I'm the first author when there are many of them, but that was a case where it was true. It's work with Fernando Quiros and Juan Luis Vasquez. Vasquez. Okay, so it is motivated by a literature that you can find now, which is very well developed, and especially in this country, by the way, about models for tumor growth. And the first class of equations you can find in the literature are what I call cell density models. Where you describe the growth of a tissue by the the population density of cells. So the equations that are used are equations which are very close to what we encountered so far, which are cells are moving with a velocity v, and this is the input of biology compared to mechanics. These cells divide and grow. And so to derive that, to describe that, you use a Lotka-Volterra term like the Fisher equation. You can think of a Fisher equation where there is a limitation. You can think of this as a g equal 1 minus n. It's very related to what we said on the first day. So the difficulty in the modeling is to know what is the velocity of cells and what is the growth term. So here we are speaking of the cell density of tumor cells, and the background that you consider that the healthy cells are all around the tumor which is growing, and these healthy cells create a certain pressure which you take as a reference pressure, let's say 0, and the tumor cells, because they divide, they push each other and they create pressure, and this pressure pushes all the cells far away. And so the velocity v in this framework is only a result of the pressure coming from just the growth of the system. Okay, so at the beginning you can imagine that cells at the beginning are small and far away, and they begin to grow, and then they begin to touch. And at some point, these cells are themselves incompressible because these are more or less droplets of a fluid. So, okay, they can arrange maybe like that. I'm not sure you have ever seen cells like that in a tissue, but you can imagine that they go to a pressure which is maximum, and then you cannot go further. And so you create pressure, and at some point you have filled completely the space, and you reach the incompressibility limit. So all the discussion is always, is a tissue completely incompressible or not? Is there space for cells to reorganize and grow more or not? So the ingredient is simply to say that cells are pushed away by this growth. When these cells grow, this one, by pressure of this one, will move in this direction, this one in this direction. And so you know how to do that. You use the Darcy rule, which says that v is minus of the gradient p, and in the simplest case you take that p equal n to the power m plus 1, and m is a positive number which is related to the description of these kind of things. We'll come back on that later. So this is the first assumption for the motion of cells. You can also obtain the same rules departing from more elementary models with mixtures, because of course the tissue is not only cells, there are many things around. So you can also make models which are more accurate, and this you find them as simplifications or asymptotic limits. In any case, this is the simplest model. I will show at the end how you can enrich the system and what are the questions which are coming out. So this is for the velocity. So there was a long period where the growth here was related only to the nutrient available. So now you have to think of a tumor which is growing. There are blood vessels all around, and you say, okay, the tumors which are growing, which are using nutrients, so there is less nutrient, and people thought that the nutrient was the most important thing. And then there was a second period where people, based on physics, said that this growth is mainly controlled by the same pressure, which means that when cells come together, because they have sensors, these cells have sensors on their boundary, they feel the contact, they feel the pressure of the other cells just by mechanics, and this mechanics triggers some chemical reaction which blocks the pressure. So the growth you get is something like that. If I drop the pressure, I draw the pressure here, the function G will be something like that. So it will be maximum when the pressure is small. Let's call it Gm. And there is a pressure Pm for which the contact inhibition is so strong that cells stop dividing, because this triggers this chemical reaction which stops the division, the division cycle. So I think the first ones to say that are Byrne and Drasdo, based on numerical simulations. In France, there is a group, in France and Germany, by the way, there is a group of around Johanny, Prost, and Julie Scher in, I think Julie Scher is Dresden, I think. And Prost, we are physicists, and we made experiments on tissues to check that, and they arrived to the same conclusion, that the pressure, they create really a pressure, and that the pressure stops division of cells. And they get a beautiful name for that. They call it the homeostatic pressure. So they found the correct denomination for this limiting pressure.
Can I ask a question? So the station here, the first one is N, and then you have what, N, or what's that?
This is the number, it's a bad number, okay, it's M.
No, the other one. The line before. Yes, that's N, or?
Yeah. Oh, that's N, yes, the same density.
Okay.
That's N, the density of cells are moving, so it's just advection of cells by virtue.
It's like a Hileshow flow with...
and that will connect it to a Hileshow flow. Yeah, it's a porous medium equation. This is just the porous medium equation with a growth term. Okay, so this is the first class of equations you can find in the literature, and it's easy. I mean, existence is not a big problem. Existence. Okay, so I will give assumptions to make it rigorous. So our assumptions are always that the initial data is positive, or at least non-negative, and it is convenient to assume that the pressure is less than the homeostatic pressure here. So you are always initially in the growth phase. And what else do I need? So because of that, N0 is in L1, I can always assume that it is always in L infinity. I will also assume that it is in L1, and we are working in RD to simplify as much as possible. I think that's what we need right now. Okay, I will make another assumption, which is to simplify. It's not really needed, but it is much simpler if we assume that initially the tumor is growing. And these bounds, these assumptions are propagated by the dynamics. So this implies that n of xt is non-negative always, is positive always. This implies that the pressure P of xt is always less than Pm. That's simply because you have we have a maximum principle on the pressure, so it's just maximum principle, and we have that the integral of n of x and t. Of course, the tumor is growing, so this term is acting, and so there is a control which is not very good, which is by integral of n0 of x dx exponential of gmt. So that's a growth, exponential growth, which is of course not true. It's a very rough estimate of the real growth. Most importantly, and this is common with the Fisher equation, that's what we have seen at the first course. This also implies that dtn of x and t is non-negative for all times for all x. So this is, yes?
In the way you wrote it, can't you just substitute? I mean, you can substitute p by n in the equation, so there's no initial data for p, or is there?
That's correct. There is no initial data for p. And p is completely connected to n. When you know n, you give p, and when you know p.
So you made this assumption, so this is just...
These are just assumptions. This you can see it as an assumption on p.
Yeah, okay.
So p0 is just n0 to the power m. So okay, to take the power 1 over m is completely the same.
Yes. P is an elliptic variable.
P is an algebraic variable, by the way. Okay, so this is the first thing. If you want to go further, you have another estimate. So I will also assume that n0 is bv. This is, let's say, w11. And then the other estimate is that grad xn in L1 is controlled by grad xn 0 in L1 exponential gmt. And this is because of, again, of the Proust-Meillam equation. All this is known, it's just consequences of what we know from the Proust-Meillam equation. So this is the first class of equations. There is a second class of equations which you can find in the literature. And this class of equation is free boundary problems, where you say that the tumor is a given set. Let's call it omega t. So this is a tumor growing inside, growing to invade the healthy tissue, and people give a velocity here to describe the growth of the tumor. So this is a very well-defined interface, and you can compute the tumor by just moving the interface. And all this began with Greenspan in 72. So that's the thing, that's the first paper which appeared on this kind of aspect, and that's been kept for by many, by complete school, and maybe now in US, the Loven group is also working on that. Mark Chaplin is working on that, Ellen Burnham, I noticed. So many people are involved in that. So when I saw that, I asked Juan Luis, but what is the connection we can make on these two models? And as Enrique mentioned, this is through the LHO. So what is the LHO limit? How do you create a free boundary out of that? So the idea is the following. So the initial limit is a limit when m becomes very large. So if you come back to this cartoon, what you can see is that the pressure, as long as cells are far away, so the pressure is very small, the cell density is very small, means the pressure is zero because cells do not see each other, so they don't create pressure. And then suddenly they begin to touch, and then when they begin to touch, there is not so much room in 3D from spheres or things like that which touch to these kind of things which are completely realistic. So very quickly, the pressure is very high and you arrive to the maximum compaction of cells. Okay? So if you want to do that and say that this is very stiff, what you do is you take simply m equal very large in this pressure. So some people even say that at short range there is an attraction of cells because of adhesion of cells. So they even draw these kind of pictures, which we will not do because this opens up a completely different class of problems. What is the meaning you can give to this kind of pressure? So what we will do is simply look at what happens when m becomes large. And to understand that limit, what we need, so now what I will do is simply to put an m everywhere. And what we need to do is to be convinced that we can pass the limit in all the quantities which are here. So these estimates which have been written up there, you agree they are uniform in the parameter m, and then they tell you that n is BV, uniformly BV in space-time. So the first thing that you know from the limit, the first consequence or the first lemma, is that you can extract subsequences so that nm, let's keep it, or nmk, converge strongly to some n infinity, or m sub k tends to infinity. So this is the first thing. But clearly this is not enough, because you need also to pass the limit in this term. And so you need also something, so this converges strongly, at least you need some weak convergence of the gradient of p, which is not written here. So you need further estimates. And these further estimates also come from an idea which is very well described in Paulus-Monium equation, which is to work a little bit more on the pressure. So if you write using just the chain rule the equation on the pressure, so which means you derive the derivation of an equation on Pm, you just multiply by m. So pressure is defined as m plus 1 by m plus 1 p to the power m. This equation, n to the power m. This equation. Here you get exactly the derivative of the pressure. So the first term is easy. It is d over dt of the pressure, depending on m. The second, okay, now you have to use the chain rule. Here you can put the n outside. You will get n Laplace p, and you multiply that by this quantity. So what you get is minus m plus 1 p Laplace p. But then you have also to use the other term, Vm grad n. Grad m with the multiplication by that will give you grad p. And because of that, you will get grad p squared here. And then on the right, you get something which is simple. It is simply m plus 1 multiplied by p. So, which is some kind of strong form, and n satisfies really a weak form. It's really a conservative form. Here you see that you have a maximum principle very well, for example, on the pressure. This is a good equation to see that you have a maximum principle. At the maximum point, this will have a sign, this will be 0, so you control. This will be 0 if you are above the homeostatic pressure. So you understand why, very well, why you have this maximum principle written like that. So there are several consequences that you can draw from this equation. The first one is that if you just integrate by part, you just integrate. So if you integrate the pressure, you are in good shape, because the pressure is n times something which is bounded, because n is bounded because because the pressure is bounded. So from that you know that the pressure is also in L1. So if you integrate that, what you will get is the integral of the pressure at time t minus p0 dx, which is under control. Here you will get a term which will be plus m plus 1 integral of grad pm squared. This one will pay for the plus 1, it's not very important. And here you have m plus 1, something which is controlled by m plus 1 pm g sum m, the maximum value of g. Because of that, so you divide by m plus 1, this will count for 0 because m is very large and this is bounded. So what you conclude from that is that the integral of the gradient of the pressure, so this is a double integral, by the way, in time and space. So what you draw from is this. It's controlled by something which depends on time and from the initial data. So this gives you the first conclusion of that. And you can push further this conclusion because we also know that dt Pm is non-negative, just because dtn itself is non-negative and p is an increasing function of n. Then you conclude that dtm is a bounded measure because a positive distribution is a measure, and you control the total mass now by integrating this. So you integrate everything and you get the control of dtm, or you get it from the control of dtn. So this tells you that you have that dtn is a measure. That dtp, yes, the time derivative is controlled, the space derivative is controlled. So this means that Pm is converging strongly also after extraction always to a P infinity. So this is the conclusion, the second conclusion. The first conclusion, which is important, is this one, because it tells you that grad P is weakly compact. It's converging weakly in L2, and that's exactly what we need to pass the limit. Okay? So this implies grad Pm, grad x Pm converge weakly. Weakly in L2. There is no boundary. Here there is no boundary. There is just a cell density which is positive everywhere because it's a beautiful elliptic equation, and I put an initial data which is positive, and this is not really necessary. And zero. You can have a free boundary, but this is not very well defined. It's if you put it, you can find it. If you don't put it, you don't find it.
It's implicit.
It's implicit. If you put in the compact support initially, it will be. So this doesn't use the free boundary at this stage.
What is this V equals minus gradient of P? P is defined.
The Darcy law.
Yes, the Darcy law.
Yes, but for the whole, for one cell or for complete?
For the tissue, that's for the tissue. The tissue you see it as a fluid. That's really the point of view of physicists. They say a tissue is just a viscoelastic fluid. And here we forget about the viscosity. This is one of the questions, but to put viscosity in there.
Sorry. What's the first integral from down? Third.
So this is what you have, when you integrate this in time and space. So you get the different values integrated in x. Here you integrate by part.
So it says the first term is Pmx0.
Pm of x. P0 m of x.
No, the previous term Pmx
X in T.
X and t.
Capital T.
capital T.
And this is an integral from 0 to t. And this is an integral also from 2t and rd. So the global control in space and time.
You should say that all core details are on the paper in archive, so they can look it online.
Okay, so I say that all the details are on the paper in archives.
The small details are in archive.
Okay, so now everything is fine. You can arrive directly. We have all the ingredients for the theorem. The theorem says that in the limit m tends to infinity. So we said that n converges strongly. We say that the gradient converges weakly, and we say that the pressure converges strongly. So you can pass the limit in this equation, and you obtain directly d over dt n infinity plus divergence minus divergence of n infinity grad p infinity equal n infinity g of p infinity. What I claim is that you get also that n infinity minus 1 p infinity is 0. Those are functions. These are functions defined in all LP spaces. There are BV. We have BV estimate space-time, so n at least is BV. And we know that the derivative of p also are controlled in L1 or let's say in L1 log. So everything is under control in terms of what it means. So this means something in terms of distribution. This is an L2 function at least, and this is an L2 object. So everything is well defined. In fact, this is more. This is L infinity. So everything is well defined. You can pass the limit. There is no difficulty. The only thing that you get this information, which is very strange, because now you have two quantities, n infinity and p infinity, which are only related by this relation. And you don't have the beautiful algebraic relation which tells you that p is a function of n. So the proof of that is okay. So the only thing is, why do we have that? And that's simply so this relation comes from p m equal n to the power m. So if p of xt. So when let's say when m converge to something which is less than 1, and this is less than pm. Okay. So this also means that n infinity is less than 1. Because if you take, okay, from that you drove that the limit can only be less than 1. So either the limit is strictly less than 1, but if the limit is strictly less than 1, this object will be going to 0. So which means that if this is not 0, this is 0. And in the other case, n infinity equal 1, and then this is 0. So from this relation, from this equality, when m tends to infinity, the limit of this inequality is this. And this is n plus 1. Okay? So this is the limiting relation. So we have to understand. So this is not very clear what it means, this problem. It seems to be underdetermined because this is too weak. So the surprise, I think the really surprising result on that is the second theorem, which I will not prove, which is that the solution of that is unique. So I call this a weak formulation. We call this a weak formulation of Elisho problem. This weak formulation of Elisho equations as a unique solution if you put in initial data. Yes. And that is a little bit surprising because this is a weak information, and nevertheless, the solution, you can prove uniqueness. This is enough to prove uniqueness. So this is a new problem that we have to understand what it means. So what time? Okay. So certainly, the simplest is to argue heuristically. So what does it mean, this stupid equation? So basically, this relation tells you there is a set where n equals 1, and there is a set where n is strictly less than 1. So if you, or let's say more precisely, there is a set where the pressure is positive, and then n equals 1, and then pressure, a set where n is less than 1, and then the pressure. So if you define omega of t is a set where the pressure is positive, then n equals 1 in omega. So if n, and if you imagine that this set is an open set, or an open subset of omega t, because n infinity equals 1, then the derivative is 1. So what you obtain is here simply Laplace p infinity equal g of p infinity. So formally, of course, is it true or not? It's not clear, because it's not clear that you can write that the time derivative in distributional sense is 0. Also, outside omega, n is strictly, the pressure is 0. So the boundary condition is that p infinity on the boundary is 0. Okay, so this is what it means. So there is a set where the pressure is positive, where you have an elliptic equation, because you take n equal 1. And if you are outside of omega, so if you are in the complementary of omega, now the pressure is 0. If the pressure is 0, the gradient of the pressure is 0 heuristically, and this term disappears, and so now you get d over dt n equal g, and p is 0, so this is gm. time n infinity. So exponential growth by not only differential equation. So the maximum growth, which is what you obtain for p equals 0. So in some sense, you get two equations written in this single equation. You have two equations. One on the pressure, which is independent of n, because n equal 1, you don't know what is doesn't give you information on p. And then you get an information on p. Or you are in the set where p equals 0, and of course p equals 0 doesn't give you so much information, but this equation gives you information on n. So there are two informations encoded in this equation depending where you are. And now the quantities p and n, which were linked at the beginning, which were 1 to 1, now are becoming independent, controlled by two different equations depending where you are. Okay? So that's a little bit tricky. So I'm sure you don't believe me. Clearly seeing your eyes, you don't believe me. So I will show you a picture. If Vincenzo allows it, I'll show you what happens. He allows it.
So threshold 1 you have.
Oh, it's yeah.
You have just 1 in front
yeah.
of n,
Yeah, that's a normalization. If you normalize by the number you get.
So is there any, if you have a function in front of it, of g of x times n to
If you, okay, so that's, I would say, okay, so I think you would make a function of x that say locally the tissue is not homogeneous. That's an open question. We didn't look at that. It could be that.
because that brings you to show flow with weight.
Yes, then you would have weight, but it depends where you put them. So certainly you have to put them inside. So what you see here on this movie is what happens. Let me go back to the initial time. Okay, no, you don't see anything. For some reason. It's okay? Okay. So I have to, let me go back to the beginning. So this initial data is the density, is the green curve. So, so the green curve you see is less than 1. So n is less than 1 means that the pressure, which is the blue curve, is more or less 0. And of course I'm very bad in numeric, so the pressure is not exactly 0, it should be. Or this is m equal 20 or something like that. It's not exactly the limit. So, so this is the density less than 1, pressure 0. Then, so you are in the regime of exponential growth because p equals 0, n will grow exponentially. Okay, so this is what you see. The pressure grows, the density grows close to 1. When it becomes close to 1, the pressure builds up. And you see that the pressure builds up only where n is very big. And then you have a competition, which we didn't explain right now. You have a competition between the invasion, the front, where n equal 1 is moving to the right. So you see a discontinuity on n, which is moving. The pressure is building up because n equal 1, this zone. And outside, you have a competition between the front moving and the exponential growth. And clearly, the front is faster than the exponential growth and will invade the total domain. And so after some time, this kind of mushy region, whatever, as we said yesterday, where you have here a density between 0 and 1 will disappear. After some time, the front will have invaded all the initial data with compact support.
That's the limit question.
That's m equal to, where I computed with m equal to 20, more or less the limit. If it was a limit, it would be really flat, equal to 1 on the top. It's not exactly flat because it's not exactly the limit.
Before the
yes,
very large.
because I don't know how to compute m equal infinity.
Since m is an exponent, m equals 20 is immensely large.
M is very large already, yes.
So we say that infinity begins with 6.
Okay, so I think it's a little bit larger. Okay, so you understand this. So this equation So what we said explain two things. It explains the tail on the right on the border. It explains that P satisfied is like that because this is the elliptic equation Laplace P equal minus Laplace P equal G of P with the real boundary condition, something which looks like a parabola. So this we explain. What we did not explain is the front, which is invading. So the front we didn't explain, and that's the next step. How can you explain the front? And so this front is really what you describe geometrically, usually by the LHO equations. So also this I cannot erase. This is an important information. So so this is something last. Okay, so I'm a little bit lost with the numbers now. So this is, let's say, 4, the geometric motion, the geometric motion. So now what you can do is take to see the simplest case where you have this front moving and invading all the domain is to consider the case where n jumps from 0 to 1 and there is not this mushy region where n is between 0 and 1. And you would like to know if there are solutions n of xt which can be written as just indicator function of omega of t. And so what you see is that so as long as omega of t is smooth, so that you can define, you can solve this equation, that you can find the velocity and all what we need, then what you have is the following. As long as omega is smooth, then what you have is, so I write the picture rather than the formulas. What you have is that you have omega of t here. You solve this equation, minus Laplace P infinity equal G of P equal infinity inside. On the boundary, you have P equals 0. So you solve the elliptic equation and you move the boundary according to the velocity V equal minus, so the pressure is 0 here, so again the gradient is exactly, so compared to what we said in the first course, the gradient is already orthogonal to the surface, and the velocity is exactly minus dp d nu, where nu is outside normal to the domain, dp infinity d nu. So you move the velocity, you move the domain with a velocity which is a gradient of the pressure, and again, this is a non-local problem, because to compute this derivative, which is of course a local problem, you need to compute the pressure everywhere. So you need to compute the pressure in the full domain to access to this velocity. Okay, so this is a very nice example. So if you believe this, which you will show in a couple of few minutes, if you believe this is a nice example where the free boundary is directly described by a transport equation. So compared to the classification we gave, this is an example where you can do it. You write simply a transport equation of the indicator function, and you describe the free boundary completely. You can also do it, so we said that you have an equivalent formulation which is using Hamilton-Jacobi equation. You can also do it with Hamilton-Jacobi equations. You can use this weak formulation, but you can also use an Hamilton-Jacobi formulation, and this was done by one Kim in maybe 10 years ago. So you can also describe the econal equation and give a viscosity, say what is a viscosity solution for the corresponding Hamilton-Jacobi equation. So how do you see that? How do you see the? How do you see that this is the real picture if everything is going well? Again, I will do it only in 1D, like we did it yesterday. So. So you wonder in 1D. So in 1D, even what you can do is take an infinite domain, take here a point x of t, and say that this is omega of t. So n infinity equal 1 here, infinity equals 0 here, and so n of x and t is the indicator function of the set x less than x of t. And you wonder whether this can be a weak solution to this kind of equation. Okay. So if you do that, you see that when you compute the derivative, and the pressure. So for the pressure, you take the solution to the elliptic equation, which is here, which is something which looks like this. In this case, it's like this. So that's the pressure given by this equation on the half line. And when a P is reaching, so this is not 1, this is a P max, your homeostatic pressure. When P is going close to P max, this becomes close to 0, and then you are flat. So you have a traveling wave solution if you want. Okay, yes, you can see that as a traveling wave solution. You can compute the exact traveling wave solution, and that's equivalent. So if you put it in there, what you see is that here n equal 1. So this is an interval. So here it's rigorous. N equal 1. The equation is this equation. It's correct. N equals 0. So the equation is 0 equals 0. It's true. The only question is, what does it mean on this singularity? So again, you compute the derivative of this function dtn in terms of, in the sense of distribution, and what you get is simply that dtn. So now when you look in time, not in space, this is x. When you look in time, you inverse the growth. It is 0 and it jumps to 1. So there is a jump which is 1, a time derivative because you use a chain rule, and the Dirac mass at x equals x of t. So now you want to know what is this object. This object is a jump from from the gradient p here to 0. So this object, in terms of distribution, it's a jump, the derivative of a jump from 0 to gradient p. So the derivative is the Dirac mass, and the Dirac mass is exactly the term minus grad p. Here it's just the derivative in x, meaning you are in 1D at x of t, delta of x equal small x equal capital X of t. And this value is the value on the left, so at minus xt minus. So which is more or less also the rule of the Stefan problem. So very connected to the Stefan problem too. So if you put together these two objects, they have to compensate to be a solution in the distributional sense. So what you get is dp dx of x of t minus, which is exactly in 1D the rule, the geometric rule that I was describing. So all this is included in this weak formulation when it's smooth. Okay. So let me quickly give now a few questions which are puzzling in this theory. Yes.
One phase Stefan problem with zero specific
Is it really? I mean, this is this rule is a true, but the weak formulation is not. The weak formulation is not really.
Let's take the second line. Can I just replace that by n infinity belongs to the heavy side of p infinity?
Yeah.
You.
Of course, yeah.
No,
Yeah.
no, I don't agree.
Novelty is that it implies also the information about what happens outside.
Yes, that's the point. That's the point. You get more information. That it's just a free boundary. You'll get a global information of also.
Well, this problem is the one phase really short problem.
Yeah.
Yes, this one is yes. This one is correct. But there is all the weak formulation contains more. It contains both information. It contains this one and this one. So I think it contains more than.
Well, I know that it's a bit more complicated because n infinity, because you've got the heavy side inside the
Yes.
divergence, and that's what
Yeah.
makes it.
Yes, that's it. Yes. So if you know that it is an heavy side, it's fine. The heavy side solution, I agree. Okay. So heavy side solutions are yes, correct. It contains more. Okay. So, but okay. Now let me tell you So these are the easy things. Let's explain clearly where it goes afterwards. So there is a question, the most critical question which we do not understand completely is, questions. So heuristically you get that. But now we want to prove it rigorously. And of course omega of t, in principle, you don't know if it's an open set. So you cannot do that. So what you can prove is that p infinity, Laplace p infinity plus g of p infinity is 0. And you can prove it because so this doesn't make sense. Let's put it like that. If you take it like that, it doesn't make sense because this is a measure. Because you have a kink, the pressure is like that, so you have always a Dirac mass at this point. So Laplace p is nothing better than a measure. You multiply by a function p for which you don't know very much. You just bounded. So this doesn't make sense as it is. But you can integrate by part. In distributional sense, you can integrate by part and use a test function. So you multiply by a test function and you write that minus integral of grad phi p grad p infinity plus phi grad p squared equal integral plus whatever plus integral of phi p infinity g of p infinity equals 0. So this you can write, and this makes sense. So this weak formulation, the distributional sense, makes sense because this is an object which we said is in L2. So this makes sense. So we can prove it, but we can prove it as a consequence of the limit equation. So I erased the equation of p infinity. That was a mistake. In the equation of p on p m, if formally you pass the limit, you get easily that this is true. But now the question is to prove it. So what we proved, in fact, is that the gradient of pm's converge to grad p strongly in L2. And not only weakly. And because of that, you can pass the limit in this formulation and prove that this term, which is a bad term, converge. But this is not a very good proof, because this should follow from this relation, from the weak formula, from the weak LHO. So for the weak, from this, you should be able to derive that. And we don't know how to prove it. So the first question is a direct derivation from weak LHO.
The second thing is what Ricardo calls the sigma function, right? Relation P plus G plus F. Right? This is this measure.
Multiplying, yeah.
Yeah. So P times the multiplier is zero.
Yes. So that's called also. So this is not an obstacle problem, by the way.
Question for you, Ricardo.
So to make a connection with the other, also to other things, this is not an obstacle problem, it's not unique. You give me any set omega of t, I can always solve this equation equals 0 and this set omega of t with Dirichlet boundary condition, and I get a solution of that. So again, this is a bad problem. It has not the correct sign to make it unique, and of course, because you need to give rules to move the boundary, which are given by the weak formulation. So this is the first question. The second question now is that I didn't tell you the truth. Now, because you follow the course until the end, I can tell you all this is useless, and I've never been used by any serious people in cancer growth. Models are always more complicated, and what you always need, at least, yes.
Is the question here?
Here is how you prove. I give you a weak solution to that. It's unique. There is a weak. Okay. Can you prove directly that this is true? So what we can do is a little bit stupid. We can say that this weak solution is the limit of this, and we can pass the limit in this equation on the pressure to recover that, which is not very intuitive. I mean, it is not very okay. It's true. It's a truth. I mean, it's a theorem. It's all true. But we would like to have another proof, which would be
does not use approximation.
Which follows from that. So of course,
if you are strong in functional analysis, and the French are supposed to be, you prove this by brute force.
So you already proved strong converging L2, right?
it's already proved. Yes, we know that.
So this should
We know and from that we can pass the limit in this term and get it.
By intimidation.
So yes,
directly from
yes.
If you approximate,
Can one, for any solution of this VHS, show that there exists a sequence that converges and solves the previous equation? It's not, I mean, backward.
So maybe okay. No, maybe depending on the initial condition you put, some of them are not obtained as the limit of the others. It might be that there are things like that. Because for uniqueness, especially for uniqueness, we need conditions. So all the technical details on the paper, it's more than initial data in between 0 and 1. We need also, if I remember, some BVS, so some BV property. So maybe there is a, yeah.
if the data are adaptive, things go very well. If they are not adaptive, there is a transition layer.
Repair.
Yeah. Repair.
And so this is the first class of questions. The second class is indeed if there are weak solutions with weaker assumptions. But the real problem now, which are going from application, is the fact that usually you don't have a single equation. You have systems. And typically, if you put a nutrient, what you want to put is an equation like that. The nutrient is consumed by the cells, and let's say is released by blood vessels. So there is a parameter lambda, which tells you what is the release of oxygen, of glucose. And you may have several nutrients, by the way, not only one. And you multiply the first equation just by putting the C in the growth term. Okay, so it's a linear coupling. But now everything becomes more complicated, and one way to see that is that this property I used, that dTn is positive, is completely wrong. Because this is Rowley maximum principle, which has to do with the fact that you have a single equation. And this is wrong. And this plays a very important role in this. In this thing, it's very important. And so all the structure disappears. This doesn't hold, we don't know how to prove it. So even though formally, if you change that, you just change the equation by putting this. And if you do the algebra, this is true. We don't know if it's true. So the second question is C infinity. Let me tell you that there is another variant of that, which is that cells are moving only by pressure. It's true, but it's not always true. Cells can also move by active motion. So it's also true that some cells, and that depends on the cancer, the most invasive cancers are cells which can move. And these are those who are very problematic. They create metastasis. And this is represented by an additional term here. Okay? So that's something we did also with Fernando Quiros, with Nicolas Vauchelet, and Mintang. And again, what you can do is derive a weak solution. In that case, we can prove that this is true when there is no nutrient. And the same rule is true, which is surprising. You put viscosity on the top of it, N becomes smooth, and still you get the same Eléchaux equation here. So these are variants. There are many other variants which I don't know how far they are. I didn't have time to look precisely. But cells here are all dividing. In practice, you need to include also cells which are quiescent, which do not divide. Most of the cells in a cancer do not divide. If you count, but just by a simple calculation of the number of cells and the time of division of a cell, if all the cells of a cancer was dividing, in a few days your entire body would be filled. In fact, a big part of them are quiescent. And these quiescent cells, they do not divide. They are pushed by the pressure, of course. So you should write an equation also on the quiescent cells. So you should have another equation on the quiescent cells. Okay, and then you get a system with 3 equations, and then you get new difficulties because these cells will exclude each of them. So you have these segregation problems which come in. Where you have N, you don't have Q. When you have Q, you don't have N. So you have more things which come in the game. And then you open a new class of questions. And if you look at the literature, it's amazing how many variants you have. And all of them are technically difficult and up to my knowledge are not treated. Okay, so this is a field, I think, where there are many questions staying to be solved. Okay, stop it. Thank you.
Thank the speakers who have completed their jobs, and in fact, Benoit has been eating up from part of this open session discussion because the last part is